So today we're going to talk about trig verifications, and the difference between a verification and an identity, if you will, is an identity is more of a simplification. Take this expression and break it down so that it's in its simplest form, whereas a verification says, I have this expression and here's what I want it to look like in the end. So let's take a look at our first example. We see we've got the following trig expression. We want to verify that this is equivalent to sine squared. This in some sense is like a simplification because it goes down to one term. So I want to change all this and do something that will get me just sine squared. I know I have a Pythagorean identity on top and a Pythagorean identity on bottom. On the top, 1 plus tan squared I know is secant squared. So secant squared minus 1 is equal to tan squared. And 1 plus tan squared, like I said before, is secant squared. So you'll notice on top I have a subtraction, on bottom I have a singular denominator. One of the tricks I commonly use is I split these up into two separate fractions. So this is secant squared x over secant squared x minus 1 over secant squared x. Keep in mind I want to get this to sine of x. I know secant squared over secant squared is 1. I know 1 over secant squared, well, that's like cosine squared. And here's another Pythagorean identity. 1 minus cosine squared is sine squared. And you'll notice that now this quantity is equal to what I wanted. One of the things about verifications is you may only work with one side of the equal sign. You can't work on both sides. It's kind of like a geometry proof where it says, given this, prove this. You can't use any of the prove in order to get to the end of the problem. Just like in verifications, only use one side. So once you pick one side, you're stuck. Let's look at the next example. So we want to show that this quantity is equivalent to tangent. Right, and I will go through and change a little bit. The difference here in this problem is I don't have any trig or any Pythagorean identities. So I'm going to change everything to sine and cosines. This is what I typically do when I have a problem like this. So I'll take sine of x plus tangent's equal to sine over cosine. So what I'm going to create is a complex fraction. And that's equal to 1 plus cosine of x. I don't like the complex fraction, so I'm going to take and multiply both the numerator and denominator by cosine of x. So in the numerator, I have cosine x, sine x, plus the two cosines reduce, you'll notice, because I'm distributing through. So I have sine x left. And I'm going to leave this for right now. Cosine of x times 1 plus cosine x. And I'm going to show you why I left it as is. I see ahead of time I'm trying to reduce this to sine over cosine in the end. And I notice in my numerator I have a common term of sine that I'm going to factor out. So if I factor sine out of the top, I'm left with cosine x plus 1, which just so happens to match up with the cosine x plus 1 in the denominator. Now you'll notice these are opposite. However, since it's addition, I know addition's commutative, and these two will reduce out. This gives me sine x over cosine x, which we know is tangent of x, and I'm back to where I wanted to be. So that's been verified. Look at the next example. Again, we're going to show this is equal to secant of x. I have no Pythagoreans, change everything to sines and cosines. So in this first term, I have sine of x over the cosine of x times the sine of x plus the cosine of x. And I want to get this all equal to secant of x, which is 1 over cosine. I notice now that I have sine squared over cosine plus cosine. I'm going to need a common denominator. So if I need a common denominator, I have to have a cosine on the bottom of this term. So cosine over cosine I'll multiply by. I get sine squared of x plus cosine squared of x over cosine of x. There was my common denominator. Hey, look at the top. I've got Pythagorean identity, sine squared plus cosine squared. That's equivalent to 1 over cosine of x. And 1 over cosine of x is equal to the secant of x. And once again, that's where I wanted to get to. Next example. Now you'll notice I'm going through these, pretty quick because I know all my identities and I know how things transform. You have to do enough of these to be able to recognize all these Pythagorean identities. The bottom line is get your Pythagorean identities down. All right, now, this is the first case where I don't have a singular term I'm trying to verify. So in other words, I'm not trying to get this rational function into one term. I'm trying to get it into two terms. So I got to think ahead a little bit. What I want is cosecant squared minus secant squared, which isn't an identity. Looks like one, but it's not. I know that cosecant is 1 over sine and secant is 1 over cosine. So if I can get 1 over sine squared minus 1 over cosine squared, I'm happy. Now this term looks a little ugly. It doesn't have any Pythagorean identities in it, but I'm going to try again and change it to sines and cosines. So cotangent is cosine of x over sine of x. Tangent is sine of x over cosine of x. And this is all over sine of x, cosine of x. Now again, this is a complex fraction. Usually in complex fractions, I'll take and multiply by the LCD of the numerator and denominator. Notice the denominator here is 1. So I'm going to multiply by sine of x, cosine of x to both the top and the bottom. And I have to do it to the top and the bottom because that's like multiplying by 1 and it doesn't change any values. Distributing this in, my sines go in the first term, I get cosine squared. The second term, I get sine squared over sine squared x, cosine squared x. And we look at the top and we go, hey, is that an identity? It's actually not. Sine squared plus cosine squared is 1, but cosine squared minus sine squared is not an identity that we know of at this point. All right. But I do notice, well, hey, look I got some things that do match up on the top and bottom. I just can't reduce because of the subtraction sign. But what I can do is that trick I showed you earlier in the day, whereas if I have a subtraction or an addition on top and a singular denominator on bottom, I can split it into two fractions. So what I'll do here, I'll say this is cosine squared of x over sine squared of x, cosine squared of x, minus sine squared of x over sine squared of x, cosine squared of x. And you'll notice right off the bat now that these cosine squareds reduce, leaving me with 1 over sine squared of x minus sine squareds reduce 1 over cosine squared of x. 1 over sine squared is cosecant squared of x. And 1 over cosine squared of x is secant squared of x. And that's exactly what I wanted to get. All right, so now we have a situation where I have, again, two more complicated terms that I'm trying to verify. I can pick either side or the other. Usually when I have a multiplication to do, I'll start working with that side. So let's go ahead and do that. I'm going to FOIL this out. So this is cosecant squared of x minus 2 cosecant of x sine of x plus sine squared of x. Now, you'll notice here, cosecant times sine, that's like a term and its reciprocal. So that's just a simple value of 2. So we have cosecant squared of x plus sine squared of x minus 2. And I've got to get that equal to this term over here. Now, I need a cosine squared, and I see I've got a sine squared here. So I know sine squared is equal to 1 minus cosine squared. I can make that identity happen right now. So let's do this. Let's say this is cosecant squared of x minus 2 plus 1 minus cosine squared of x. And that comes from the sine squared identity. Now you'll notice I have 1 minus 2, which is negative 1. So I have cosecant squared x minus 1 minus cosine squared of x. I need the cosine squared of x, which is a negative. Cosecant squared minus 1. 1 plus cotangent squared is cosecant squared, so cosecant squared minus 1 is equal to cotangent squared of x minus cosine of x. And that's what I was looking for. So it's very important, once again, that we know our identities. All right, here's an example. No Pythagoreans in the problem, but I've got an addition of 2 fractions. So what I'm going to do is get an LCD. So let's do that. My lowest common denominator in this case is going to be tangent and secant plus 1. And I'm going to rewrite that twice. And make 2 fractions so we all know what's going on. So since I know that's my common denominator, this first term here is going to need to be multiplied by secant plus 1 over secant plus 1. Second term is going to need to multiply by tangent over tangent. So when I do that, I'll multiply this out. That's secant squared of x plus secant minus secant. That goes to 0 minus 1 plus tan squared of x. 1 plus tan squared is secant squared. So secant squared minus 1 is tangent squared. That's an identity. And that's all over my LCD. And I still am not quite sure how I'm going to get to all this sines and cosines. Probably in the end I'm going to switch everything to sines and cosines. So right now, when I add this together, I have 2 tan squared of x. That's a bonus because I have a 2 in my problem now. Over tan of x times secant of x plus 1. All right, I'm getting to the point where I'm going to have to take and start figuring out a way to get this reduced even more. Remember, I'm trying to get everything equivalent to 2 sine of x over 1 plus cosine of x. So in order to do that now, I'm going to take and start reducing. I notice the tan squared and the tan. Well, this is actually just a tan, right? Reduces to 2 tangent of x over, the tans are gone, secant of x plus 1. I need it to be 2 sine of x. Well, the only way I'm going to get this to sine of x is to change tangent to sine over cosine. So let's do that. 2 sine of x over cosine of x. And I might as well change the secant to 1 over cosine of x. Once again, I have a complex fraction. I'm going to multiply by the LCD of both the numerator and denominator to both terms. So in doing that, what do I end up with? I end up with 2 sine of x in the numerator. In the bottom I have 1 plus cosine of x. And if I'm not mistaken, that's exactly what I'm looking for. There we have it. Let's do another one. All right. Now, remember in the beginning I said we can't use both sides of the equation. And in this problem, we notice I have no Pythagorean identities. I have nothing I can change to sine and cosines because everything's already in sine and cosine. When you're in this case where you have no other option, what you want to do is take and multiply by the conjugate. Remember from radicals, the conjugate was the same first term and the opposite of the second term. So in this case, I'm going to multiply by the conjugate. Whoops. Let's change this up a little bit. I'm going to multiply by the conjugate of the denominator of this first term. So that's 1 minus cosine of x times 1 minus cosine of x. So this gets me sine of x times 1 minus cosine of x. I'm going to leave that. I'll show you why in a second. Notice what I get in the denominator. I get 1 plus cosine minus cosine goes minus cosine squared of x. Now you'll notice in the denominator, 1 minus cosine squared of x, that's a Pythagorean identity of sine squared of x. That's all under sine of x times 1 minus cosine of x. The signs go. I'm left with 1 minus cosine of x over sine of x. What do you know? All right. Today was a challenging day. My recommendation to you is get all your Pythagorean identities down and understand the relationships between all your sines, cosines, tangents, cosecant, secant, and cotangents. The quicker you can do that, the more successful you're going to be at these identities. So here are a couple of verifications I want you to do. I won't be able to give you an answer to fill in. In fact, I don't even want you to put an answer into the form. Just do these, and then I will have these answers worked out for you tomorrow up on the board so you can check them. Okay? Best of luck.